Log on, tune in, find out. Another good idea from Cambridge.
We will speak about energy preserving numerical integration.
Okay, well, it's wonderful to be back here in Cambridge, but I do apologize that due to family circumstances I have not been able to prepare a talk specifically for this meeting, so I apologize to those people that have heard me speak on this topic before. I'll talk today about preserving energy, and in particular energy for Hamiltonian systems, both ODEs and PDEs. And my collaborators are mentioned here: Reinout Quispel, Volker Grimm, Robert McLaughlin, David McLaren, Dion O'Neill, and Brynjulf Overen. And well, actually some other people have also collaborated on smaller parts of the talk. And it is indeed particularly nice to be talking about this here, because the main formula that I'm going to be showing you was sort of discovered here in this building 3 years ago. So, and we've been working on that ever since. So it's been, that meeting on highly oscillatory problems has been very productive as far as we're concerned. Okay, so as I said, the outline of the talk will be, actually I sort of don't need to walk to the computer. The outline of the talk will be, first part will be energy preservation for ODEs, and then the second part will be energy preservation for PDEs. So I'll start with the beginning. So let's assume that we have a, let's see, where do I find chalk here? Poisson system. I'll just write this here for future reference. So we have dx dt, so x is a vector, equals sx times the gradient of some function h. So this matrix has to be skew, and this is the Hamiltonian function, and this is just the standard gradient. And well, I guess everybody probably knows what a skew symmetric matrix is, but I've written the definition here, and that's for later comparison when I'll be talking about operators, and you'll see that the definition is very analogous. And the whole sort of, I guess, theme of the talk will be that PDEs are very similar to ODEs in the sense of energy preservation. All right, so let me just go back one slide. So if you look at this formula, or the one that's on the screen, I'm going to be discretizing every part of this formula in order to preserve the energy. So how do we preserve, or how do we discretize this part? How do we discretize this part? How do we discretize this part? And how do we discretize that part? So the left-hand side, this skew symmetric matrix, the gradient, and the Hamiltonian. So the first thing that I do here is a definition of discrete gradient, and that's sort of the most, in a sense, the most crucial ingredient. So our definition is given here. So the discrete gradient is denoted by a bar over the gradient. So this means discrete gradient. You can denote it by this bar. And the first thing is that the discrete gradient depends on, well, maybe I should first write down what is going to be my discretization of the left-hand side. That's going to be xn plus 1 minus xn divided by, say, a time step. Or maybe I think better stick to tau for the time step. So xn plus 1 is my new point, and xn is my old point. And so you see here that this discrete gradient depends not just on one point, but on 2 points. So that's sort of a difference from the if you like, the continuous gradient. And then the definition is given here. The dot product of xn plus 1 minus xn with the discrete gradient should be the value of the Hamiltonian at the new point minus the value of the Hamiltonian at the old point. And this turns out to be the ingredient that you need. And you might think of this as the discrete analog of, say, dx times the gradient of h equals dh, right? So this is a continuous analog that we've discretized here. And then, of course, you want some consistency. So in the limit that the new point and the old point are close together, the discrete gradient should go to the continuous gradient. Okay, so that's the definition of if you like, this part together here. Because for the time being, so I should say that, okay, well, I'll come back to that in a minute. All right, so what I claim now is that this discretization here, instead of tau, I've used delta t here. So I just don't do anything with this Q matrix S, that this discretization is energy preserving. Now actually, it is not very difficult to show, and here it is. So by definition of the discrete gradient, the difference between the Hamiltonian at the new point minus the Hamiltonian at the old point is the discrete gradient dot product with this. But if xn plus 1 minus xn satisfies this equation, then I can replace this by that, and so, or times delta t. And so we get discrete gradient times S times the discrete gradient. And now because this is a skew matrix, it's symmetric in these discrete gradients, the whole thing has to be 0, right? So the crucial ingredient is really that this matrix S is skew symmetric. Okay, so, well, just to go back to this definition, here it is. So you will note that this discrete gradient, just as the ordinary gradient, is a vector. But this vector here is defined by a scalar equation. So that means that, say, if you're in 10 dimensions, you only have to satisfy one equation. So that means there's a lot of freedom in how you choose this discrete gradient, even if you have to satisfy this. So here are going to be some examples. I'm only going to give 2, but actually there turns out there are infinitely many possibilities if you only have to satisfy that constraint. Now here's the first one, which is due to Ito and Abe, I don't know, maybe 15 years ago or something like, maybe longer, in a slightly different context, but related. So the first component is just h at, well, if you look at this carefully here, it's just the x that is shifted. Well, yeah, I should be a little bit careful here. Before I used x as a sort of a vector, and here I use that so that xn has components xn and yn in 2 dimensions. So I hope you don't get confused. Sorry, I just have a shift in x here, and then divided by delta x. And now the only sort of unusual thing here is that, well, the y is shifted, but also this is at the new xn plus 1. And so now if we use that definition, which is up there, and we take the dot product with this vector, which now is the vector xn plus 1 minus xn, yn plus 1 minus yn. So the first component is multiplied by this, so the denominator disappears, so I just get this minus that, plus this minus that. And then you see if you add that up, this cancels against that, so I just get h at the new point minus h at the old point, which is exactly what I should get. So this is sort of like a harmonica, it sort of all fits together. And well, maybe you can see then immediately that, of course, you can do this in any dimension in a similar way, and otherwise that's sort of a little exercise. You can try it at home. All right, so this is one way to do this. It's okay, but there is also another way to do that, and that is the so-called average discrete gradient, which basically, remember that the bar denotes the discrete version, but here this definition involves an integral of the continuous gradient from xn to xn plus 1. So this integral just means that, well, I should probably do that over here. You have the point xn here, and a new point xn plus 1 over here, and then you take an integral over a straight line path from the old point to the new point. Of course, you don't know the new point, so this is an implicit method. Let's see what has happened here. Oh, I've already skipped ahead. So, all right, well, now I'm going to show that this formula also satisfies this definition. So I take the dot product of this discrete gradient with xn plus 1 minus xn, and then it should equal the right-hand side here. So take the dot product. Well, I can take that dot product inside the integral because it doesn't depend on this psi, which is the parameter along this path. And then you see that, so the beauty of this whole thing is that this, here you have, if you like, xn plus psi times xn plus 1 minus xn. So this whole expression here is nothing else than dd psi of this. And now we have the integral over psi of a derivative with respect to psi, so you just use the fundamental theorem of calculus. So this is this expression evaluated at psi equals 1, where this disappears, and this is h of xn plus 1, minus the same expression evaluated at psi is equal to 0, when this disappears, and here we have h evaluated at xn. So this is just the right-hand side that we needed. And just to mention that this formula was used in numerical work by Lex and van Leer to do with shock waves, so it was not directly related to preserving energy. Okay, so the upshot is we can use this as a discrete gradient. So in my formula there, which is the continuous equation, I replace the gradient here by this discrete gradient. The s, oh, this should be s of xn. I just can leave as it is, and this is just the Euler quotient. So the statement is that this is an energy preserving integrator for this ODE. All right. Well, so what? Okay, so well, it turns out that this particular discrete gradient has some nice properties. And one of these and in particular, if we now restrict, and from now on in this talk I will restrict, you don't have to, but for the purpose of this talk I will restrict to the case that this Q-symmetric matrix is constant. So that includes the so-called canonical Hamiltonian structure. So if that is the case, this S now no longer depends on X, so I can put it in here, but I could always put it in here. But the point is now that then S times this discrete, S times this continuous gradient is equal to this, to the right-hand side over here, because, but, or maybe I should write it down. First, let's say we had, I'll write it here. We had the case that S depended on X. So you'd have this, grad H at psi, what have I got? Xn plus 1 minus psi xn d psi. If this S depends on X, then you can see the argument here is different from the argument there. So in that case, this product does not represent the vector field. But if this is constant, then this whole expression is nothing else than f evaluated at this point. And that was sort of my eureka moment in 2007. Because if that is the case, we can just write the method like this. And now all of a sudden, this is defined for any vector field, whether it's Hamiltonian or not. Right? It just so happens, if it is Hamiltonian, then this method will preserve the energy. But I can also apply this to dissipative vector fields. So now it turns out this numerical integration method now knows sort of intuitively when it needs to conserve, when there's an energy to be preserved, right? I don't have to tell it what the energy is. If there is an energy, it will preserve it, at least for a constant symplectic structure. Not only that, but since the method now depends on the vector field without any splitting or anything like that, it turns out this is a so-called B-series method, and the whole theory of rooted trees and so on applies to this, and we've done a lot of work on well, looking into that, which I won't go into this during this talk, but it turns out that there's well, it's sort of an analog of the whole theory of symplectic B-series methods and Runge-Kutta methods. All right, but now back to where we are now. So the result says that this numerical integration method preserves the energy H exactly for any Hamiltonian ODE of this form where F is equal to that. So let me give an example of a simple Hamiltonian ODE. This is the simplest kind, 1 degree of freedom. And yeah, well, I haven't written down what the Hamiltonian is here, but it's sort of fairly simple. It's kinetic plus potential energy. And it turns out if you use that formula that I gave before, you get this expression. Because of course, just to going back, yeah, keep switching forwards and backwards. This is a little bit of a strange numerical method, right? This is or unusual. And normally, you don't have, say, in your Runge-Kutta methods, there are no integrals over the vector field. You have sums, and you can evaluate at different points. But here, this is turns out that well, John Butcher has looked at this sort of more general kind of thing. But still, what if you don't know what this integral is in closed form? But let's look at the simplest case. If this f is polynomial, then of course this is just a polynomial in psi, and you can integrate it exactly. The same if it's trigonometric. If it's not, well, then it's a little bit harder. But then you can, for instance, use quadrature, and then it turns out that if you approach or approximate this to a certain order by a quadrature, then energy will be preserved to that order. And what is even more, if you, for instance, if your quadrature is correct for all cubic polynomials, then this will, then that approximation will be exact for cubic vector fields. So it turns out that you can actually preserve polynomial Hamiltonians by specific Runge-Kutta methods. But there's not one Runge-Kutta method that will preserve all polynomials. For different order polynomials, you have to get more and more complicated Runge-Kutta methods. But anyway, so in general, we have this expression which involves the integral. So that's sort of a novel kind of integration method. Okay, so that I'm about halfway, and so now it's ready. I'm ready to get started on the second part, which is, well, how do you do similar things for PDEs? Well, I guess I'm just going to cheat a little bit. I'm just going to do a semi-discretization, and then I will be left with a lot of, with a system, a large system of ODEs, and I just use my old method. But there's a little bit more to it than that. Okay, so let's say, what's my definition of a Hamiltonian PDE? For simplicity, I will just look at scalar, mostly at least at scalar equations. So I have du dt is some function f of u, but now it can of course also depend on spatial derivatives. And for simplicity, again, in the talk I just will talk about one spatial derivative. Well, that is Hamiltonian if it is of the form s hat times the variational derivative. Now look, that's very similar to what we had here for the ODEs. Except what's the difference? S here was a skew symmetric matrix. S hat here is a skew operator in general. This was the gradient. This is the variational derivative. But it turns out those are, in a sense, in infinite dimensions, the exact analogs of what we had over there. So what? So this is what I said. Yeah, usually it's real. We can also look at complex cases such as Schrödinger equations. Okay. So here, for those that perhaps are not familiar or have forgotten, what is the definition of a variational derivative? Well, here I just do it for the simple case, so you can of course give a more general definition in arbitrary number of dimensions. So it's just the variational derivative of h with respect to u is just a partial derivative, then minus the d dx of dh dux. So this is the kind of thing that you see, for instance, in Euler-Lagrange equations, right? So this turns out to be the analog that you need to show that you have that energy is preserved in this case, so because you use integration by parts and so on. And so here you see the definition of a skew operator, which is very similar to what I wrote down before for a skew matrix, except that this inner product is different now. This should actually read B here, that this inner product is now defined as the integral over the real line, whereas of course for ODEs this is just a sum, sum AI b dot bi. All right, so now we know what the variational derivative is, we know what a skew operator is. These are the ingredients that we have over here. So then the question is, how do I do my semi-discretization in order to get back to the situation that I was in before? Just trying to see where I can find an eraser. You found one? An eraser. Oh, here they are. Yeah. It's actually about 6 erasers here. Okay, so now let me write that du dt equals s hat times the variational derivative of curly h du. All right, so how are we going to discretize that? I will show you that in some examples. So I'll start with the simplest example, or one of the simplest examples, which is Sine-Gordon equation. So first of all, we write that as a, because it's a second order equation, we write it as a system of equation. And the Hamiltonian here in the continuous case is just given here, where this pi is the momentum associated to phi. And then here actually the reason this is the simplest case is that this operator here is still just a matrix. So this is a matrix, but now in function space, right? So in the space phi, where phi and psi are the variables. Okay, so how am I going to semi-discretize this in order to be able to apply my previous integral preserving method? Well, actually it turns out there's various ways. So the first way I'm going to do that is I'm going to just do this phi dx just by a backward difference, which I've done here. And that's all. And so instead of one phi and one psi, we've discretized it, now we may have 1,000 components to phi and 1,000 components to pi. So my matrix S is now, has this form, where this is now a 2,000 by 2,000 matrix, right? Whereas before it was a 2 by 2 matrix in infinite dimensional space, or in function space if you like. And now it's a large matrix, but in a finite dimensional space. And then the variational derivative is then in the semi-discretization just replaced by the gradient. And the simplest way to think of it, if you look at this definition, once you have semi-discretized, there are no derivatives anymore. So the only part you have left is this, which is the gradient. So, well, maybe a bit hand waving, but it's a way to think about it. Okay, so here I show you what. And then so now I've semi-discretized it, and now I'm back in the case where I was before, because now I have S, which is a skew symmetric matrix, times the gradient of a Hamiltonian. Yeah. Okay, so now we can do this, and we've compared here. The blue one is our energy preserving method, and we compare it with the midpoint rule, both second order methods, and you see that they're very comparable, except that here the energy is preserved exactly. And the global error is also fairly comparable. All right, now let's see a slightly, now just to show you that there's an enormous freedom, that here I did this discretization of H, but I can also do, for instance, instead of backward differences, here I do symmetric differences. That doesn't make a difference. Ari, are you sleeping? Okay, well I'm glad to hear it. So this should be phi n plus 1 minus phi n minus, so there's a little misprint here. So we can do this one with symmetric differences, and it just gives very similar results. All right. Now let's look at a slightly more challenging example, the KdV equation. Why is this more challenging? Because now this operator S hat is indeed an operator. It's a differential operator. So I'm going to again discretize this. Here I do the standard discretization. U cubed is just replaced by un cubed. Later on I'm just, for the heck of it, going to replace it by un times un plus 1 times un plus 2, just to show you that there's a lot of free. I'm not saying that that's better, but you can use this freedom to try and optimize some other properties. Now the thing here is, remember that before this du dx here, I can use symmetric differences or backward or forward differences, it all doesn't matter. But this matrix S, there it does matter, this ddx. So here, this ddx here is basically, say, un plus 1 minus un minus 1 divided by 2 delta x. And the reason I have to do that is because otherwise, if I just use, say, backward differences, it wouldn't be skew symmetric. So that's the main thing that you have to be careful with, that your discretization of this operator must, or whatever this operator is for the particular PDE, you must always have a skew symmetric discretization. Whereas here in the H, it doesn't really matter. As long as it's consistent, it will be fine. Okay, so here, let's see, what am I showing here? Oh, the exact solution. Well, yeah, the reason I show it, you might say, well, why isn't this the exact solution? Well, this is due to the spatial discretization, which of course, that's independent of the temporal error, so you can independently make this as small as you like, which we'll do in another example. Okay, so here, as I said, here now we do a slightly different one. Now I do, just to show that it still is just as energy preserving as before, I do use this discretization, but the same skew discretization for S. You could use other discretizations, like including, say, further differences, but as long as it's symmetric, or well, skew symmetric. So that's what I wrote down here. There's a large freedom in the semi-discretization of H, but the S must be skew. So here is this slightly unusual discretization of the cubic term. Okay, so complex equations, of course, you can also do. The Hamiltonian here is this. Here the S hat is again just a matrix. And we just need to discretize this, which you can do, of course, in a variety of ways. Here I've just done the standard differences. So here, let's see on the right hand, sorry, here's the energy. Of course, in our energy preserving method, there's no error in the energy, at least in the spatial, or in the temporal discretization, whereas the midpoint rule is, of course, this is a small error, but there is an error. On the other hand, which I'll show in a minute. So for the global error, they're very similar. The only thing is that what, for instance, the midpoint rule does better is preserve the total probability, because that's preserved by symplectic methods, and which is not preserved by this by this particular energy preserving method. Okay, so just also to show a non-integrable example, and also a slightly different discretization. Here we use Gauss, Lobato, Legendre, with, well, here are all the details for those. This can all be done. So the point is the semi-discretization, there's lots of ways you can do that, as long as you well, stay in the general framework of having a skew symmetric matrix times the discretization of a Hamiltonian. So here's some pictures. Let me see, what else have I got next? So here is the energy error. Of course, our method doesn't have an energy error, and here's some MATLAB routine. Okay, well, I'm not going to show you this movie for two reasons. I've shown it before here, and also I've run out of time. So, as I said, for the spatial, you can also use spectral discretization. It will all work fine. We've also applied it to linear PDEs. The ordinary Schrödinger equation, Maxwell's equation. You can also generalize it to the case that instead of a skew symmetric or a skew operator, you have a negative definite operator. Instead of energy being preserved, then your energy will monotonically decrease. It's a so-called Lyapunov function, and that, for instance, applies to these equations. So if you want to make sure that your energy will always decrease, for instance, when there's only a very small decrease in energy, some numerical methods will not preserve that, but you can with these methods. Well, I didn't go into the details, but there are generalizations of this which can preserve any number of integrals, not just the energy. But if you want, say in the KdV equation, you want to preserve the second and third invariant, that's also possible. Well, this I've mentioned. B series I've mentioned. Here are a few references, but by no means all. Our esteemed chairman, for instance, has written on generalizations of this work, and so have others. And then, of course, there's a school in Japan that has done a lot of work on this. So thank you very much.
Other questions?
Yes, Tim.
Okay, still all the concern. Seems skew symmetric is so important, so adaptive methods in space will cause problems because non-uniform grades to be used for different subpopulations.
Yeah, I think we've discussed this before. I don't know that it needs to be a problem, but maybe we should discuss this together in more detail.
The second thing is, how about the boundary conditions? Suppose one-dimensional problem left and right, different boundary conditions. That would destroy some symmetric problem.
Yeah, no, mainly this work is for, which we've done is for periodic boundary conditions. Yeah. It's a good point.
Is this merely first order in time? This
no, this method is second order in time.
second order in time.
Yeah, but there are generalizations which are higher order in time.
So it's possible to achieve higher order and maintain the conservation.
Yes.
Thank you.
Please.
Well, is it reversible in time, your scheme?
Yes.
Get the same error, you don't
Yes.
get anything.
It's symmetric forward and backward in time. Yeah. So it preserves, in particular, it preserves all linear symmetries and linear integrals and foliations. Yeah.
Okay. So thank you once more.
Okay, thank you.